Differential equations are used to model all sorts of phenomena found in nature, and one example is the discharge of a capacitor in an electric circuit. The other is some structure subjected to a blast, and you can see that we need to make approximations to be able to model these phenomena. And another example is the complex behavior of ocean waves. And here we'll focus on first order differential equations, which basically relate the function and its first order derivative. So in this case, Q, the discharge of a capacitor, is a function of time. And we'll demonstrate solution methods to solve first order differential equations as we go. And note that differential equations can also be used to model the growth of a deposit, the rate of change of a chemical reaction, and so on. And we'll also see that in several examples. You may be given a verbal problem to interpret as a differential equation, and here I've just given you a picture for this first problem to give you a visual. Now a particle is attached to a spring which is stretched and released. So as you can imagine, if you grab this block and pull it to the right, you're going to stretch that spring. And then when you release the block, it's just going to oscillate back and forth. Now the particle's acceleration is proportional to its position, and the constant of proportionality is minus omega n squared. And we're asked to write the differential equation that models this situation. Well, in the horizontal direction, the particle's acceleration is the second derivative of its position with respect to time. And that's proportional to its position, and the constant of proportionality is minus omega n squared. And here the position x is a function of time. And this is our differential equation that models this situation, which you may recognize if you're taking physics. We can use differentiation to verify if a function is a solution to a differential equation. And this is best illustrated with an example. So here we have q of t as a function of time, and every other term is constant. So on the left hand side, we take the derivative, so this term drops out because it's constant, and differentiating the exponential term, we obtain the following expression. Now on the right hand side of the equation, we substitute for q, which gives the following expression. And now we can cancel out these terms, and therefore this expression becomes positive because the negatives cancel. And therefore these expressions are equal, which means that q of t is actually a solution to this differential equation. Let's verify that x is a solution to the following ordinary differential equation. So if we differentiate x with respect to time, and noting these are constants, well, we get omega by a cosine omega t plus phi. And then differentiating this again, we get the second derivative of x with respect to time is equal to minus omega squared a by sine omega t plus phi. And what you do is substitute with the second derivative and x into this ordinary differential equation, and you'll see that the left hand side is equal to the right hand side. So therefore x is a solution to this ordinary differential equation. A slope field is a graphical representation of a differential equation, and it's plotted on a finite set of points in the plane. And it tells us how solutions to first order differential equations behave. So we can see that for y greater than 0, the slope field is all negative. And for y less than 0, the slope field is positive. And for y equals 0, the slope is all 0. And as we can see, as we move along x and keep y constant, the slope field is constant. So therefore, C is the correct answer, because for negative y the slope field is positive. And we'll get some practice in sketching the slope field using tables in the following problem. Let's draw the slope field for this ordinary differential equation. So what you do is write the derivative in terms of x and y by subtracting 2x on y from both sides, and then you substitute for different values of x and y. So we have x in this direction and y in this direction in a table. And you get the following values for the first derivative y dash in this table. And then what you do is plot these at different parts of the graph. So for example, at x equals minus 2 and y equals minus 2, the slope is negative 2. So it will look something like this. And at x equals minus 1 and y equals minus 2, the slope is negative 1. So it looks something like this. And another example is if we look at x equals minus 2 and y equals 0, the derivative is infinite. So it looks something like this. And if we keep doing this, for every point, the slope field looks like this. Solutions to differential equations are functions or families of functions. And later when we analyze differential equations in more detail, you'll see that this differential equation represents exponential decay, and when we learn how to solve it, it has the following solution. So some constant by e to the minus x. So as we can see, when the constant is equal to 1, we have e to the 0, and then the solution curve follows a slope field. So you can see that we can estimate the function by following the slope field. And another example is when that constant is equal to minus 1, then according to this differential equation, minus negative values are positive. So we get positive slopes along this curve, and just following the slope field, you'll be able to sketch the solution curve. So as you can see, we have a family of solutions, and we'll get some practice in sketching these solution curves in the following example. Let's use a slope field to sketch the solution through the point 0, 2. So as we can see, the slope of the tangent to the solution curve is 0 at this point, and then if we follow the slope field, well, what we have is something like this, which follows a slope at the next x value. And if we keep following the slope field, the curve looks something like this. And on the other side, we can do the same. So you're not going to be 100% accurate, but that looks reasonable. And you can sketch another solution curve. So for example, through 0, 4, that's a bit easier to sketch. So you have a 0 slope, and then you follow the slope field as best as possible. So the solution to the first order differential equation given by this slope field is a family of parabolas. We can use Euler's method to approximate a solution to a differential equation, or find a point on the solution curve. So to find an approximation for yi, we start off at yi minus 1, and we add delta x multiplied by the slope of the tangent to the curve at yi minus 1, which is the derivative. And that'll give us delta y, and therefore our approximation to yi is yi minus 1 plus delta y. And as we mentioned, delta y is equal to delta x by the slope of the tangent to the curve at xi minus 1. So you can see that the larger delta x is, the worse our approximation is. So this is the exact value, and this is our approximate value. So you're going to get a larger error as delta x becomes larger. So what we do is use smaller divisions to approximate yi using several steps. And we'll see that in a coming example problem. Let's use Euler's method to approximate y of 0.4 using this differential equation where the initial condition is given and the step size is given. So let's write Euler's equations and the initial conditions. And now we can start our steps. So when I equals 1, x1 is equal to x0 plus delta x according to this equation. So that's 0 plus 0.1, which is 0.1. And y1 is y0 plus delta x by y dash 0. So that will be 0.2 plus 0.1 by minus 0.2, which is 0.18. And therefore the derivative, y dash 1 is equal to minus y1 according to this differential equation. So that will be minus 0.18. And now you can set I equals 2 and then calculate x2 and y2 and y dash 2 using these previous values and keep stepping through until x is equal to 0.4. So you can calculate y of 0.4 and post your answer in the comments. We can solve first order differential equations of this form using separation of variables. So we call this a separable differential equation because we can divide through by gy on both sides and multiply through by dx. So therefore we've separated the variables x and y, and then we can thereby integrate both sides of the equation and then solve this equation to obtain y as a function of x. And note that when we evaluate these indefinite integrals, we're going to get some constant of integration. So therefore y of x is going to depend on the value of that constant, and that constant can have an infinite number of values. So therefore we call y of x a general solution to this separable ordinary differential equation, or a family of solutions. And we'll apply this technique in the coming example. Let's find the general solution to the following differential equation. So what we're going to do is put it in a form where we can separate the variables. So dy dx is equal to sec squared x multiplied by y. And now we can separate the variables. So we have dy on y is equal to sec squared x dx. And now we can integrate both sides So on the left hand side we get the natural log of y, and on the right we get tan x plus a constant of integration. And now we can take e to the power of both sides, so therefore we obtain y is equal to e to the power of tan x by e to some constant, and this is just another constant, so we can write y is equal to some other constant by e to the tan x. And that's our general solution, which you can differentiate and substitute back into this equation to verify that it satisfies the original differential equation. Recall that for a separable ordinary differential equation, we can separate the variables by putting the y terms on one side and the x terms on the other side. And that allowed us to integrate both sides of the equation, and therefore on the left hand side we get some antiderivative of the reciprocal of g of y, so I'm just going to call that h, and that's equal to the antiderivative of f of x plus a constant of integration. And then given that y is a function of x, we solve this equation for y, so effectively what we get is y of x is equal to some function of x plus c, which is a constant. And this is the general solution because we can have an infinite number of values for the constant c. So therefore what we do is apply an initial condition and then solve for the constant of integration, and then we substitute it into here to obtain a particular solution to the ordinary differential equation. Let's find a particular solution to this ordinary differential equation. Well, we're given an initial condition, and then we're asked to compare y of 0.4 using the exact solution. So what we're going to do is put this in a form where we can separate the variables. So therefore dy on y is minus dx, and then integrating both sides, we obtain a natural log of y is equal to minus x plus a constant of integration, and therefore y is equal to e to the power of minus x plus c, which is the same thing as e to the minus x by e to the c. And because this is just some constant, then we can write y is equal to some constant by e to the minus x. And now we can apply our initial condition, so therefore the constant of integration is equal to 0.2. And therefore from this equation, our particular solution is equal to 0.2 by e to the minus x. And now you can substitute for x equals 0.4 and compare it with the approximate solution we got using Euler's method. A skydiver's acceleration is described by the following ODE, where g and k are constants, and we have an initial condition, and find the equation for the velocity as a function of time. So we have the acceleration is equal to g minus kv, and we can separate the variables and then integrate both sides. So on the left hand side you can use u substitution, so what you'll get is minus 1 on k, while the natural log of g minus kv is equal to t plus the constant of integration. So you have the natural log of g minus kv is equal to minus kt plus some other constant, and if you take e to the both sides, we get g minus kv is equal to e to the minus kt plus c1, which is the same thing as e to the minus kt by e to the c1. And this is just some other constant, and now you can easily solve for v, apply your initial condition, and write the particular solution, and post your answer in the comments. Exponential growth and decay can be modelled using the following ordinary differential equation, which states that the rate of change of a particular quantity is proportional to the size of the quantity. And this quantity can be the concentration of a reactant, the mass of a radioactive isotope, and so on. So when we look at exponential growth, the constant of proportionality is positive, so the instantaneous rate of change of y with respect to time is equal to some constant k by y. And applying an initial condition y equals y0, then the solution to this ordinary differential equation can be obtained as follows, using separation of variables. So we can see that the quantity y is exponentially growing at a rate k. Now the model for exponential decay is similar, which can be written as follows, and applying the initial condition in a similar way. So in this case, the quantity y is decaying at an exponential rate k. A cash deposit D grows exponentially, so we recognize that the rate of change of the deposit with respect to time is proportional to the deposit. And therefore we can separate the variables and integrate both sides. So what we get is the natural log of the deposit is equal to the rate by time, plus a constant of integration. So therefore the deposit as a function of time is equal to e to the rt by e to the c, which is just some other constant, multiplied by e to the RT. So the initial deposit is $4,000, so we have 4,000 is equal to C1, but we substituted for T0. And to calculate how big the deposit is after 10 years, we can use the interest rate. So substitute at 2%, which is 0.02 per year, multiply by the time in years, which is 10 years. So therefore this quantity is dimensionless, and therefore D of 10 is equal to $4,885.61. Our population grows exponentially, so the rate of change of the population with respect to time is proportional to the population by the rate constant k. And we're asked to determine the size of the population after 8 years. So if you solve this differential equation, what you'd get is the population at time t is equal to the initial population by e to the power of kt. So this is a particular solution. And then applying our condition over here, well, what we have is 150,000 is equal to the initial population, which is given in the question, multiplied by e to the power of the rate constant by the time. So that would be 3 years. And then you can solve for the rate constant, which is going to be in units of per year, because if you multiply by the time t, this quantity is going to be dimensionless. And therefore if you substitute for a time of 8 years, you'll be able to obtain the result, because we know the rate constant and the initial population. A radioactive isotope undergoes exponential decay, so the rate of change of the mass of the isotope with respect to time is proportional to the current mass of the isotope. And k is the constant of proportionality, or the rate constant. Now we have an initial mass of 15 kilos, so when you solve this differential equation, you're going to get the mass at time t is equal to the initial mass by e to the negative k multiplied by t. And given that we have 1/2 of the mass decaying after 245 years, so what we have is the mass on 2 is equal to 15 by e to the minus k by 245 years. And then solving this equation, you'll be able to get the rate constant k, which is going to have units of per year. Because when we multiply by time, this quantity is going to be dimensionless. And then how much of the isotope will remain after 700 years? Well, what you do is plug in 700 years into this equation, and you'll obtain a mass in kilograms. And post your answer in the comments. A chemical reactant is consumed at an exponential rate, so the rate of change of concentration with respect to time is equal to minus the rate constant by the current concentration. Now we have the initial concentration, so if you solve this ODE, you'll obtain a particular solution of 3.0 molar by e to the minus the rate constant by time. And we're told that the concentration drops to 2.5 molar after 4 minutes, so you can plug in 2.5 here, a time of 5 minutes, and you'll solve this equation and you get your rate constant in units of per minute, such that the exponential quantity is dimensionless. And then from that you can calculate the concentration when 10 minutes have elapsed by plugging in a time of 10 minutes in this equation, and a time at which 1/2 of the concentration is left over is obtained by plugging in 1/2 the initial concentration into this equation, and you'll get this time, which is known as the half-life. The logistic growth model is similar to the exponential growth model, so it has this term that predicts indefinite population growth at an exponential rate. But the logistic model also has this second term that accounts for the carrying capacity C, or the resources available to continue to support the population growth. So when the population is much less than that carrying capacity, then you see that initial exponential growth, and as the population approaches the carrying capacity, you see this asymptote. So therefore what you get is an inflection point where the population growth slows down as the population size approaches the carrying capacity. When we have an initial population size that's larger, then you don't get that initial exponential growth, because this term becomes dominant based on this initial condition. And in the coming examples, we'll solve this ODE and verify these properties of the solution. Let's find a particular solution to the logistic model for population growth with the following initial condition. So what we can do is divide by C, the carrying capacity on both sides, and set the dummy variable W to the population on the carrying capacity. So we can rewrite this equation as the W dt is equal to Kw by 1 minus W. And now we can separate the variables, so we get dW over W by 1 minus W, and that's equal to K dt and then integrate both sides, taking the constant outside the integral. So on the right hand side, we're going to get kt plus a constant of integration. And on the left hand side, I'm going to leave it for you to use partial fractions to evaluate this integral, and then apply your initial condition, so the initial population at time 0, and back substitute for the dummy variable w, and post your answer for the solution in the comments. Let's verify that the carrying capacity is the limiting value of the solution to the logistic model, regardless of the initial population size. So to show that, we want to take the limit of the population as the time goes to infinity. So what we can see is that when t goes to infinity, we get a limit of infinity on infinity, so we can apply L'Hopital's rule. So differentiating the numerator, we get k by the carrying capacity by p naught e to the kt. And in the denominator, the constants drop out of the derivative, so what we get is k p naught e to the kt. And we can see that k is going to cancel, p naught is going to cancel, and the exponential terms will cancel, so therefore the limit evaluates to the carrying capacity, regardless of the initial population. For the logistic model, we'll derive an equation for the time at which the maximum growth rate occurs. So to do that, we want to obtain the second derivative of the population with respect to time, so that equals k dp dt minus 2kp on c by dp dt. So we'll use implicit differentiation. And then if we set the second derivative to 0, so what we get is k by dp dt multiplied by 1 minus 2p on c. So for this equation to be satisfied, for an arbitrary rate of growth and a non-zero rate constant, then the term in the brackets must be 0. So therefore we obtain p is equal to half the carrying capacity when that second derivative is 0. And therefore if you equate this equation to half the carrying capacity and solve it, you'll obtain T max. And now calculate T max for each case and post your answer.